Hi, today we're going to learn to calculate the pH of a strong acid solution. So remember that a strong acid is something in which equilibrium lies all the way to the product side of the reversible reaction, or in other words, is something in which the acid completely dissociates. So in our standard example of HCl, we have HCl completely turning into H plus and Cl minus, and there's no HCl left. From a stoichiometric point of view, if you start with a 0.2 molar solution of HCl, you're going to end with all of it turning into H plus and its conjugate base. So you'll have a 0.2 molar solution of H plus and a 0.2 molar solution of Cl minus. So let's use that information to find the pH of a strong acid solution. And this is a three-step process. First, we're going to find the molarity of our acid solution and basically just pick it out of the problem. Second, we're going to assume that because it all dissociates, our H plus concentration in the solution is going to be equal to the molarity of the acid that we created. And third, we're going to use the equation pH equals negative log of H plus to calculate the pH of the solution. So let's try that on a problem. What's the pH of a 0.0325 molar solution of HNO3? So first step, remember, is to find the molarity of the acid solution in the problem. So there it is, 0.0325. The second step is to assume that our H plus concentration is equal to the molarity, which is 0.0325. And then third, we're going to use the equation pH equals the negative log of H plus. So let's plug our H plus concentration into that. We get the negative log of 0.0325. So run that through your calculator. And you see that the pH is 1.488. Now, a note about sig figs. When you do sig figs for a log problem, basically the number of sig figs you have in your original figure, which in this case is 3, is going to be equal to the number of digits you have after your decimal point. Okay, let's go the other way. Let's convert from pH to H plus. So let's take our original pH equation and let's just do some manipulations. I'm going to divide each side by -1 to get the negative pH equals log of H plus. And now we're going to take the anti-log, in other words, do 10 to the power of each side. So then we have H plus equals 10 to the minus pH. Let's use that. 10 to the minus pH equals the H plus concentration. Now, it's really easy to figure out what your H plus concentration is if you have a nice round pH number. So if you have a pH of 4, then your H plus concentration is going to be 10 to the minus 4. If you have a pH of 8, your H plus concentration is going to be 10 to the minus 8. But what if you have something like 5.75? What does 10 to the minus 5.75 even mean? Well, put it into your calculator and calculate it, and what you'll get is 1.78 times 10 to the minus 6. So what's the H plus concentration for an acid solution that has a pH of 4.27? Well, let's take our equation, let's plug in 4.27 for the pH, and we get 5.4 times 10 to the minus 5th. Now, if you're not sure whether the answer is correct and you'd like to check it, just know that 10 to the minus 4.27 is between 10 to the minus 4th and 10 to the minus 5th. So is this between 1 times 10 to the minus 5th and 10 to the minus 4th? It is. So that sounds right. All right, so I told you when I introduced P notation that there were multiple things that we looked at in P notation, and here is your second thing. We've already looked at pH. Now we're going to look at pOH. And pOH is the negative log of the OH minus concentration. Now you can imagine that when we're dealing with a base solution, this is something that might be pretty useful. But there's only one problem, which is that it can't be measured directly. You have to calculate it from pH. So let's figure out how to do that. We're going to go back to our KW equation. H plus times OH minus equals 10 to the minus 14th. What we're going to do here is take the log of both sides. So we have the log of this product equals the log of 10 to the minus 14th. So we can simplify this if we use log rules. Let's do the right side first. The log of 10 to the minus 14th is just going to be negative 14. For the left side, remember that the log of two things multiplied is going to be the log of the first thing plus the log of the second thing. So that gives us this. Now I'm going to multiply each side by -1. And when you look at this, what you see is that we have the negative log of H plus, which is pH, and the negative log of OH minus, which is POH. And so what we get is pH plus POH equals 14. So we're going to use that to figure out the pH of a strong base solution. So a strong base is one in which 100% of the molecules that go into solution generate OH minus ions. And we're going to use that knowledge and the equation that we just derived to come up with a way to calculate the OH minus concentration of a solution. If we rearrange this, we can see pH as a function of POH, and now we can use that to come up with a method for calculating the pH of a strong base solution. If you look at the first three steps here, they look exactly like the steps for calculating the pH of a strong acid solution, except we've subbed in OH minus concentration for H plus concentration. And then the fourth step, the one we didn't have before, is to use the relationship between pH and POH. So let's try a problem. We need to find the pH of a 0.254 molar solution of KOH. And first we have to look in the problem to find the molarity of the base solution. So this is something that you would probably calculate if you were, weighing out a mass of KOH on your balance and mixing it into a known quantity of water. We assume that the OH minus concentration here is going to equal the molarity, 0.254 in this case. And then we're going to use the equation POH equals negative log of OH minus. So let's plug our OH minus concentration into that. Negative log of 0.254 will give us a POH of 0.595. But that's the POH, it's not the pH. So let's go to step 4 and use our equation. Plug in the POH, and we get a pH of 13.4. So this is a pretty basic solution. So there are these simple mathematical relationships that help us to figure out how concentrations of OH minus and H plus are related to each other, and how pH and POH are related to each other. And we're going to use those a lot as we get into more mathematical relationships in acid-base solutions. I hope this was helpful, and I will see you again soon.